Full report. My name is Connor. So the lab investigates the distance dependence of the bar magnet's magnetic field to verify the Biot-Savart law. The primary goals are to measure how the magnetic field magnitude decreases as observation location moves farther from the magnet, to calculate the magnet-specific dipole moment, and to create a 3D computation model for the comparison within experimental data. So the model's principles in physics. The core principle is the Biot-Savart law, modeled by the dipole moment formula. B is equal to mu naught divided by 4 pi times 1 over r cubed times 3 times mu dotted with r hat times r hat minus mu. We model the distance dependence as the magnitude of B bar is equal to k times r to the n, where n is theoretically -3 for a dipole. Key assumptions include treating the magnometer chip as a point and the magnet as a perfect dipole, which is most accurate when observation distance is large compared to the magnet size. I aligned my phone with the Earth's magnetic north in Atlanta to zero out the x component of the magnometer, and the magnet was placed east-west, making its field orthogonal to the Earth's for isolated measurement. I located the internal magnometer chip by finding the position of the maximum X field and the minimum Y field. This setup ensured the on-axis field was measured primarily through the X component. The experimental data through the target magnitudes were R20 was 0.231, R70 was 0.151, R120 was 0.126, the R170 was 0.113, and R1220 was 0.104. The logarithmic regression in ln of bx versus ln of r yielded an experimental slope of -2.894. This value confirms the expected inverse cube relationship as calculated magnetic dipole moment mu for this specific magnet is 1.839. Using GlowScript, I visualized the field with 7 vectors, 2 on-axis orange, 4 perpendicular cyan, and 1 at 45 degrees magenta. At an observation location of 0.264, the model predicted the field of 21.5 microteslas. My experimental corrected being that at the same distance was about 69.7 microteslas. The difference is likely stems from experimental magnetic interference or slight inaccuracies in identifying the exact sensor location. We have change this mu value here. There's the function there, and then I'm setting all the arrows down here. When you run the program, you can see the 2 orange arrows are on axis, the 4 perpendicular arrows, and then the 45-degree angle here. And then here's the data that we have. All the data we collected for the experiment and the off-axis field down here, all the calculations, and then there's it plotted on the graph. So here's the what if questions. If the setup were not aligned with the north, Earth's field would have added a horizontal component to my X readings, skewing the dipole moment result. Sticking 2 magnets end to end would double the total dipole moment, but would not change the n equals -3 distance dependence. Conclusion. So in conclusion, the experiment successfully confirmed that a bar magnet's field decreases with the cube of distance by comparing experimental data to a computational model. I was able to verify the Biot-Savart law and determine that the magnetic moment of my specific bar magnet to be 1.839 A times m squared. And thank you for listening.